All right, we're back. So now we want to talk about this wave-particle duality thing a little bit more. Why would electrons stay in these orbits? We know that they have to be in these orbits so that they don't end up in the nucleus and canceling out with a proton. And we know that they have to be in these orbits because of the emission spectra that we get from hydrogen and the other atoms. But why? Why should they be in these orbits? Well, if light can act like a wave and a particle, so like X-rays versus photons, then why can't electrons? They can. Electrons also act as both a wave and a particle. So let's think about electrons as waves. If an electron is acting as a wave, that means that it is orbiting the nucleus and it has to move in wavelengths that fit the circumference of the orbit. So let's look at that. So this black line here is the orbit, the circumference of the orbit, and the red is the that is made when the electron moves. So the electron is moving like this, but it's going in a circle. And that means that the wavelengths have to fit in the circumference of the orbit. They have to match up or this will happen. So on the right here, we have what happens if the wavelengths don't match up. If they don't match up, then the electron is going to have destructive interference with itself, and you're not going to get a stable wave created by the electron, and you're not going to get a stable motion of the electron in that orbit. So the physics says that the electrons acting as waves have to have wavelengths, have to move in wavelengths that fit the circumference of the orbit. So they could be, wide waves like this, or they could be like really, smaller waves, just so long as they match up. Which means that 2 pi r is the circumference of our circle, of our orbit, and the wavelength has to be an integer multiple of that circumference. So if we divide the wavelength by a certain number, it has to come out to the same as the circumference. So n, again, like it has been all day in these videos, has to be an integer. So n equals 1, 2, 3, so on and so forth. Whole numbers bigger than 0. So that means that the electrons are acting as waves. We can show it because it makes sense based on this orbiting theory we have of electrons. In fact, all matter can act like particles and waves, and they're governed by this equation. So the wavelength is equal to Planck's constant over the mass of the particle in kilograms times the particle velocity. So let's look at those units. So Planck's constant is joules times seconds. We've got kilograms down here and meters per second. So what's going to happen with those units? Let's find out. So we're going to end up with, so joules are equal to kilograms times meter squared over second squared. So I'm going to rewrite it over here. So kilograms meters squared per second squared times seconds above kilograms meters per second. All right, so on the top here, this joule seconds cancels out to get kilograms times meter squared over seconds. So we get rid of our second squared in the denominator from joules. And now kilograms are on top in the numerator and the denominator, so they cancel out. And then what else do we have here? We've got seconds in the denominator of the numerator and the denominator of the denominator, so they cancel out. And finally, we've got meters in the numerator of the numerator and in the numerator of the denominator, so one of those cancels out, and our answer is going to be in meters, which is just what we want for wavelength. Meters, nanometers, whatever, but for now, it's in meters. So wavelength in meters is equal to Planck's constant divided by the mass of the particle in kilograms divided by particle velocity in meters per second. That's how that equation works. And we can see evidence of that if we look at something called X-ray diffraction or electron diffraction. So on the left, we have X-ray diffraction of a titanium atom. So they shot they shot X-rays at the titanium atom, and they got this cool diffraction pattern where you see, circular orbits in there, which correspond to the waves. When we do it with an electron, we shoot electrons at the titanium atom instead, we see very similar concentric circle patterns. So if the X-ray, which is definitely a wave, doesn't have a whole lot of particle behavior, and the electron, which we typically think as a particle, if they have similar diffraction patterns when we shoot them at an atom, then that means that the X-ray can act like a particle and the electron can act like a wave, even though they don't seem like it. So we have some physical evidence of the fact that all matter can act like particles and waves. But there's a caveat there in that only particles on the quantum scale, so very, very, very tiny, like electrons and photons, only those particles exhibit waves with observable wavelengths. So waves that end up on our EM spectrum, our electromagnetic spectrum, which goes from gamma waves, gamma rays, all the way up to radio waves, if you remember back to the last section. Let's see what that looks like. So here's a practice question. Sorry, this is 3.5. Got a little messed up. What is the wavelength associated with a 1.00 kilogram baseball traveling at 30.0 meters per second? And this is our equation. So this is called the de Broglie wavelength. I should have mentioned that. The guy who came up with this concept of electrons traveling in waves and the concept that all matter can act as both a particle and a wave, his name was de Broglie. And we often call the wavelength associated with these, with Planck's constant as the de Broglie wavelength. So let's see what the de Broglie wavelength is for this baseball. So wavelength is equal to Planck's constant, so 6.626 or 6.63. You don't have to use as many sig figs as I do. Times 10 to the negative 34th joules seconds divided by 1.00 kilograms times 30.0 meters per second. And we showed that when all of these units cancel out, we end up with meters in our answer. So let's plug it in and see what we get. So when we plug that into our calculator, I got that lambda is equal to, or wavelength is equal to 2.21 times 10 to the negative 35th meters. And to show that that is not a wavelength that is observable or even measurable on our electromagnetic spectrum, a gamma ray, which is kind of looks like a Y. It's probably not the best gamma you've ever seen. But the gamma ray, which is our smallest type of electromagnetic radiation that we can measure, has a wavelength of lambda equal to 100 picometers, or somewhere less, but probably not less than 1 picometer. And 1 picometer is equal to 10 to the negative 12th meters. So we are, let's say, negative 23 or 23 orders of magnitude smaller than that. So definitely not measurable wavelength, which makes sense because you don't think about waves traveling through the air when you throw a baseball, right? So that's just to show you that, sure, everything has a wavelength associated with it. Everything can act as a wave, but not in ways that are actually practical, okay? Awesome. So that's it for today, and I'll see you in class tomorrow.